Okay, good morning. Wow, good morning. Oh, okay, good, much better. Happy Friday. Okay, so today we're going to look at two sections at the same time, 7.6 and 7.7. We're still talking about integration. What else could we be talking about? But we're going to be doing something a bit different than what we've been doing lately. We'll be using tables and other kind of approximation techniques. So let's first look at these integration tables. In the back of your textbook, and it's also in the ebook on WebAssign, you want to look at reference pages 6 through 10. There are about 120 integrals there. So let me show you what they look like. I printed them out. This is reference page 6. It's got a few things that we know. We've been using a lot. A few things that we could do with trig substitution. But here are the results. That's 6. 7 has the same kind of thing. 8, 9, 10. Okay, so these are things that we'll be using to help us integrate stuff that we cannot integrate easily or we cannot integrate at all. And you have to memorize every single one of them for exam. That's a joke. Okay, so let's start with an example that we have seen before. Number 71 on that integral table is the one that you have seen a few times lately. Right, integral of secant, the cube of secant. And according to the table, it's 1/2 secant u tangent u plus 1/2 natural log of secant u plus tangent u plus c. So back then I told you this is the kind of thing that you would look up, and it is in the table here. And the nice thing about tables, these entries in the table, is that u here is a variable. And it could be anything. It could be an x. It could be something more complicated than x. So for example, if you would like to integrate this integral here, and you look at that, and if you look through all these integrals, the closest match you would find to this one here is this guy right here, the one that contains the cube of secant. That's the closest match you could find. But as you can see, these clearly don't match 1-to-1, at least the way it stands right now. So very often, these things involve some kind of substitution. Possibly multiple times, but often one time is all we need to do. So notice what happens if I want secant cubic of one thing. So the clue I have here is, let's start with u equal to 1 over x and see where that leaves me. And if u is equal to 1 over x, then we know that du is negative 1 over x squared dx. Okay, and then we're going to sub this into here. Let me start that on the next page. I'm just rewriting the substitution we made. And as you can see, this turns into secant to the power of 3 of u, and 1 over x dx is negative du. I'll put a minus sign out here and put a du in here. Then we have exactly what entry number 71 says we can do with, right? So according to the integral table, we get negative of 1/2 secant of u, but I know what u is. Tangent of u, again, I know that u is 1 over x minus 1/2 natural log of secant of u plus tangent of u plus some constant. Okay, and so that's the integral that we wanted to solve. Questions? Get a basic idea of how this works? You look up a formula, you make it fit, and then you get an answer. Okay, let's look at continuing this theme of making substitution. Let's look at the next one here. Here we have cosine of x over sine squared x minus 4. And again, let's look at these tables here. Notice they are organized according to form. Forms involving a squared, which is a constant, plus u squared under a radical. Right? We don't have a radical here, so that's not going to apply to us. Here we have forms involving a squared minus u squared under a radical. That's not going to be applicable. Again, not applicable here. A plus bu, that might be possibly what we need, but notice that the variable is not squared, but we have a variable squared. So that's probably not exactly the right fit. And then we got these other trig ones. We have, let's see, sine up to a bunch of different powers. None of them is looking like what we wanted to look like. Inverse trig, not what we got. Exponential, logarithmic, hyperbolic, and this. So none of these fit yet. Let's go back to the first block here. When you do your homework, everything you need is here. It's one of these 120 integrals. So look at entries 19 and 20. We have, let me blow this up a little bit. There we go. Look at entry 19 here. Variable square minus, constant square minus u squared, variable squared. And 20 is a variable squared minus a constant squared. Look at what we got here. Oops. Back out. Here we go. So do you agree that number 20 looks like it could lead us somewhere? At least the form is right? Variable square minus a constant square. That looks like the closest we got. Let me rewrite it here. By the way, we could do this without using a table. How would you integrate this? Yeah. Partial fraction, yeah, that's right. Is that the only way to do this thing? How about a trig substitution? We could do a trig substitution to get the same result too, but it takes more effort. Yep. Okay, so we need to make this fit. So if you just look at them the way they stand, it's suggesting that we're going to let u be sine of x. And we'll try that and see where that takes us. And right here, this is telling us that this will work. If this is u, then du is cosine x dx. And that's the excess parts we got. Those turn into du, and now everything looks perfect. And 4, of course, is 2 squared. Then the formula says it's 1 over 2a, 1 over 2 times 2, natural log of the absolute value of u, u is sine, minus a over u plus a plus some other constant c. And there we go. All right? So as you can see, as long as you can make the right substitution, these are usually very, very easy to do. The only mistake you could make is copying down the stuff incorrectly. Let's do a couple more. Natural log of 5 plus radical x all over radical x. Okay, again, you look at your table here. We got a log in here, and I think I remember seeing a section involving log. So exponential and logarithmic forms, 96 through 102. And 96, 97, 98, 99, they're all exponential and sine and cosine. That's not going to be applicable. Now we got these 3 here to try to work with. The last one has natural log in the denominator. That's not what we got. So we're down to 2. We got 100 or 101. So as you can see, we need to make it look like natural log of u, and possibly with something else. So we're going to start by making that look like just natural log of u. How would you do that? Seems pretty obvious, right? We make a substitution. U equal to, what do you think? Right. So then there's our natural log of u. And now we just hope that these guys turn into du, and then we are in good shape. Okay, du, therefore, 5 goes away, of course. So we get 1/2 x to the minus 1/2 dx, or 1/2 radical x dx. And now this is perfect. We have radical x down here and dx. Those turn into du. That's what we got. We got a constant 2 that doesn't really matter at all. And here's our ln of u. And dx over radical x is 2 du. So that's 2 natural log of u du. And according to the table of integrals, it says integral of natural log of u is u ln of u minus u plus some constant. And now we just do reverse the substitution. U is 5 plus radical x, natural log of that, minus u plus some constant. And of course, you could simplify this further if you want to, but WebAssign is pretty tolerant when it comes to form, so this should be good enough to put directly into WebAssign. Okay, questions about the general process using these things? Pretty easy stuff. Yeah? Okay. Before we talk about approximate integrals, just want to let you know that these 120, this is a very small subset of all the integrals that we know. In fact, what I brought in here is a book on nothing but integrals. So let's see, what do we got? So we got these guys. Keep going. There's more stuff. Look at that. Look at that. Look at that. Just look at it. Okay, so there's a whole lot of integrals. And this book is a small subset of all the integrals we know. There's a much bigger book somewhere. But for the homework that you're going to have to do, these 120 will take care of all the problems that you will see. You just have to think about how to make, what substitutions to make it fit into the formulas you see. Now let's talk about approximate integrals. Okay, the idea of the tables is that it helps us to integrate stuff that are hard to integrate. Approximate integrals is to help us get an answer for something that we simply cannot integrate. That we cannot at least do by hand. And this is also how computers calculate integrals. You know what Wolfram alpha is? What's that supposed to mean? Okay, so when you put an integral in the Wolfram alpha, I mean, the computer doesn't really know that integral of x squared is x cubed over 3. It doesn't know that. What it does is it use techniques similar to what you will see today to calculate these integrals. Much more sophisticated ones, but we're going to look at the basics of how that is done. If you can understand what we're doing today, what the computer is doing is simply something more sophisticated, more user-friendly than some of the techniques you will see. Okay? Now, one integral that you will often see is this one. We can do e to the x, we can do e to the 2x, we can do e to the 3x, but we can't integrate e to the x squared. In fact, if you look up what this is in Wolfram alpha, it will tell you the answer is this. All right, so this is from Wolfram alpha. Please use it responsibly. Okay, so what is this Earth I thing here? This is something that mathematicians had to make up to describe the integral of that. And this is not a function like sine of x that we can calculate pretty easily. This is something that we have to look up in a table. So this book has a table for this function. And this thing is called the imaginary error function. So that's my point here. Some of these things we simply can't integrate. We have to still somehow know the answer of an integral of e to the x, for example. By the way, in many applications, we actually see this a lot. And when you integrate e to the minus x squared, this is just a regular error function. Okay, this integral shows up in probability and statistics a lot. So if you ever take a stat course, you'll see this thing all over the place. And you have to deal with this error function. That you got to look up a table. Okay. Now, for instance, if we want to know the answer to this integral from 0 to 1 e to the x squared, and we don't have things like Wolfram alpha, for example, and in the table there you're not going to find this thing either. How do we at least get something that's close to the real actual value if we could look up, say, for example, the error function? And we're going to look at 3 methods. They're all based on the Riemann sums. midpoint rule, the trapezoidal rule, and Simpson's rule. It's named after Homer Simpson? No. Okay, it's a guy named Thomas Simpson. Now let's here. He lived in the 1700s. Okay, these are all based on Riemann sums. Riemann sum says we calculate the area under a curve by using rectangles to approximate. So let me show you one at a time how these things work. So let's use e to the x squared as an example. It looks something like that, right? Say this is 1 and this is 0. And as an example, let's say we use 4 sub-intervals to approximate. Just like in using Riemann sums, you have to decide how many rectangles you want to use. So you divide this interval into n sub-intervals. We're going to use 4 here as an example. Okay, so this is 0.5, 0.25, and 0.75. The midpoint rule says we're going to look at the first sub-interval here. We're going to use a rectangle that's as tall as the midpoint in the sub-interval to determine the height. So the first rectangle, the height comes from x equal to 0.125, and y is equal to e to the 0.125 squared. And then we continue doing that. The middle one, the second one here, we're going to go to the midpoint, which is what's halfway between 0.25 and 0.5. I have it written down 0.375. So there's the rectangle. And then we keep doing that. This is 0.625. And then the last one, .875. And then we add up the areas of these rectangles, and that's going to be approximately equal to, in fact, you can see in this picture, it's probably going to be a very good approximation. Because, for example, the one that we shouldn't be counting is more or less going to fill in the one that the little triangle we are not counting. See that? Same thing here. This one we're counting, that's extra, kind of fills in here. So I would expect the approximation to be pretty good. So let's find out what the midpoint rule tells us this should be equal to. We simply add up all of these rectangles. The first one has a height of e to the 0.125 squared. And they all have the same width, right? The same width being 0.25. So that's the height. This is the width. Height 1, width 1. Plus height of the second one, e to the 0.375 squared, 0.25 for the width again. And we continue doing that. .875. And you add these up, get a calculator. I did this beforehand. It's 1.4487, there and about. Okay, so that's an approximation, remember. But based on the picture we drew earlier, it's probably going to be not so bad. And if you're not happy with the approximation, how would you improve that? Yeah, shorter, skinnier, slimmer rectangles. So slimmer and more rectangles, right? And in the limit, when you use rectangle that's so slim that the width is nearly 0, you would get the approximate answer. And that is the principle of what Wolfram Alpha would be doing when you ask a question like that. It would calculate these behind the scene using more sophisticated method than this, but same idea. Questions about the midpoint rule? Nope? Okay. Then let's look at the trapezoidal rule. We'll use the same picture. And again, we'll use 4 subintervals, just like with the midpoint rule. As the name implies, we're going to use trapezoids as our approximation shape and not rectangles. So in the first one here, you look at the point at the beginning of the subinterval and the end, and you draw a straight line there. And that's the first approximation we're going to make. That's the first trapezoid. Same thing with the second one. You look at the point at the beginning and the end, draw a straight line across, and that's our second trapezoid. And so on. The advantage here, obviously, is for shape like e to the x, the trapezoid seems to stay with the real shape closer than the rectangle, right? So for some shapes, this will give you better approximation, some, but not always. Always better approximation than midpoint. It depends on the shape. And typically, it's very hard to tell beforehand. So then the idea is the same. We calculated the area of the first trapezoid, the second one, the third one, the fourth one, add them together. And we end up getting this formula. So this is the kind of thing that you don't want to memorize. So on the exam, we'll give you these formulas. You just got to know how to use them. This is a simplified expression after you calculate the area of the trapezoids. You see these 2's all over the place because the side that's between two trapezoids is used twice. Used once to calculate the first trapezoidal area, and then again the second one, the third one uses this one twice, and so on. So these things have 2. Every single one has 2 except the first and the last boundary points. And delta x is the width, or b minus a over n. So from the left to the right, divided by how many subintervals you want to use. Delta x in this example would be 0.25, right? 0.25, 0.25, 0.25, 0.25. So that's the trapezoidal rule. And let's use this to calculate the estimated value of that integral. The book likes to use this notation. T with a subscript of 4. This means we use trapezoidal rule with 4 subintervals. And the previous one would be an M4. We use the midpoint rule with 4 subintervals. Okay, so this is what the trapezoidal rule would give us. Delta x over 2, the first point, that's the left boundary at x is equal to 0. But it doesn't get a 2. And then the next one, at x is equal to 0.25, it gets a 2. That's a side between 2 trapezoids. It gets a 2. And then another one, But the last point, the right boundary, does not get a 2. And this turns out to be 1.4907. Based on the picture we drew earlier, can you say if this is an overestimation or an underestimation? Over, yeah. Again, simply based on the picture. In fact, here's an interesting observation. The midpoint rule and the trapezoidal rule will always give you 1 over and 1 under. In other words, they have opposite signs in the errors. The error is the true value versus the approximated value. So one is overestimate, the other underestimate. It's not always easy to tell beforehand which one is which, but this is always the case. Whatever the shape is, one of them will always give you an underestimate, the other one always give you an overestimate. In this shape we're seeing here, e to the x squared, trapezoidal rule gives you over. So that means the midpoint rule gave us an underestimate. And the true value is somewhere between these two, right? And that's what the point of Simpson's rule, which we'll look at next, is about. It's to find kind of a medium between these two to get closer to the true value of the integral. Again, I'll give you graphically what it's doing and then the formula. Simpson's rule has a very important restriction. The number of subintervals you choose to use has to be even. Midpoint and trapezoidal rules don't care even or odd. But for Simpson's to work, it has to be an even number of subintervals. So same shape. What Simpson's rule is attempting to do is it is trying to fit a parabola through 3 points. So the first one, think of a parabola that goes from here to here. And then we calculate the area under that parabola. And then we use middle here, this one and this one, fit one more parabola that goes through all of them, like that. And then the last 3 points, we fit one more parabola that goes through all of them. So what we do then is to calculate the area under the parabola, the first one, and then be careful with the overlapping here, and then come to a final answer. The cleaned up version of the formula, in the book you will see looks like this. And just like in the case with trapezoidal rule, the coefficient of these terms change. The first one and last one always get 1. But then they alternate 4, 2, 4, 2, 4 until you reach the last one. And then in our example here, S4, right? We're using Simpson's rule with 4 subintervals. We get delta x over 3 times the first height without any with a number 1 in front of it. And then the next one gets a 4. The next one gets a 2. The next one gets a 4. And then the last one gets just a 1. Okay, so the middle terms have their coefficients alternating 4, 2, 4, 2, 4 until we get to the last one. And in this case, we get 1.4637. And this will be the closest one. Notice that it's somewhere between M4 and T4. And this is the closest one to the true value. As we said earlier, that trapezoidal and mid will always give you the opposite. One is over, one is under. So we don't know which is which, but Simpson's will always be somewhere between. And the Simpson's rule gains the most from smaller subintervals. In other words, higher n. So each reduction in n, say you multiply n by 2, Simpson's rule will gain the most from that in terms of accuracy, while the midpoint rule and trapezoidal rule gain something, but not to the same extent that Simpson's rule would give you. All right, that's it for today. Have a good weekend. See you Monday.